In this video, we're going to continue our focus on physical properties of organic compounds by describing the intermolecular forces that are responsible for those physical properties. Intermolecular forces are also called non-covalent interactions, and they may also collectively be called van der Waals interactions. Keep in mind that intermolecular forces are between molecules, not within the molecule. Now, the types of intermolecular forces depend on the compound. If we look at dimethyl ether, for example, let's think about the shape of this molecule because that's important in terms of overall polarity. We know that oxygen has two lone pairs, so it must be sp3 hybridized, which means it's going to have a tetrahedral shape with respect to all electron groups, and therefore it will be bent. So here's our O. We don't have to worry about the shape when it comes to the methyl groups. Each methyl will also be tetrahedral, but the hydrogens aren't going to make a difference. So if our carbon, oxygen, carbon are in the plane, then our lone pairs will be coming forward and going back. But let's think about bond dipoles. We know that oxygen is more electronegative than carbon, so we'll have a bond dipole like this and a bond dipole like this, resulting in a molecular dipole like this. So we can say that dimethyl ether has a molecular dipole, or we could say it has a dipole moment or a permanent dipole. Now let's try to think about how one molecule of dimethyl ether interacts with another molecule of dimethyl ether. And we're going to get really fancy here and represent dimethyl ether as a blob. And so we're going to have a partial negative where the oxygen is and a partial positive where the methyl groups are. Now this molecule can line up with another molecule where the partial plus of one molecule is going to be close to the partial minus of another molecule. And so when we have a permanent dipole, we have dipole-dipole interactions, where the partial plus of one molecule is attracted to the partial minus of another molecule. So our first type of intermolecular forces would be dipole-dipole interactions. So what we discussed already in terms of bond dipoles and molecular shape to determine a molecular dipole, this becomes important in trying to determine whether a certain molecule can have dipole-dipole interactions. Next, if we take a look at water, again, this is bent with respect to the atoms because oxygen is tetrahedral with respect to all electron groups. Now, oxygen compared to hydrogen, we have a really big dipole. So a strong bond dipole, leading to a molecular dipole. But in the case of water, we have an especially strong dipole. Rather than representing molecules of water as a blob, let's just write out water. But remember, we have a partial minus, partial plus, partial plus. So one molecule of water can line up with another molecule of water and another molecule of water and another molecule of water. Here's our partial minus, partial minus, partial minus, partial plus, etc. And here we have interactions between the partial minus of one molecule with a partial plus of another molecule. And these types of interactions are often drawn as dotted lines. With water, this is a special case of dipole-dipole interactions, where we have an especially strong dipole and a very effective network of interactions. And this type of intermolecular force is called hydrogen bonding. I think this is an unfortunate name because it makes me think of covalent bonding, but hydrogen bonding is an intermolecular force. So hydrogen bonding is a special case of dipole-dipole interactions, and it is possible whenever we have hydrogen directly connected to fluorine, oxygen, or nitrogen. Notice the hydrogen must be directly connected to the fluorine, oxygen, or nitrogen. Just having a hydrogen and an oxygen in the molecule is not sufficient. The hydrogen has to be connected to the oxygen for hydrogen bonding to be possible. Now, thinking back to the functional groups that we learned about, we know that hydrogen bonding then is possible, okay, with water itself, but it's possible with any alcohol or with carboxylic acids. And a hydrogen connected to a nitrogen, we have that in certain types of amines. So hydrogen bonding will be prevalent in alcohols, carboxylic acids, and some amines, for example. Coming back to dipole-dipole interactions, these are going to be possible in ethers and other amines and many carbonyl-containing compounds, whether we're talking about ketones or aldehydes or esters, for example. What about intermolecular forces in hydrocarbons? On the previous slide, we saw dipole-dipole interactions in a special case called hydrogen bonding, but hydrocarbons have no significant dipole. So what holds these molecules together with each other? So let's say this represents a hydrocarbon, so there's no permanent dipole, but we have to remember that because electrons are mobile, it's possible that the electrons can shift. So let's say for a moment, all of the electrons decide to hang out over on this side of the molecule, giving a partial minus, and then over here we have a partial plus. So this is a temporary dipole, and it can induce a shift in another molecule. So here's another molecule that's just minding its business, but as all of these electrons come over here, they're going to kind of repel the electrons, and so the ones that are evenly dispersed are going to shift over this way, inducing a partial minus, partial plus in this molecule. So a temporary dipole can lead to an induced dipole, and then this can induce a dipole in another molecule and another molecule and another molecule. Even though hydrocarbons and other nonpolar molecules do not have a permanent dipole, they can have a temporary dipole, which then induces a dipole in neighbors. Altogether, these induced dipoles lead to attraction between the molecules. So this is another type of intermolecular force, and they can be called induced dipole interactions or induced dipole interactions, analogous to dipole-dipole interactions. Here it's induced dipole, and they're also called London dispersion forces. So any of these descriptions can be used. Now let's compare a few different hydrocarbons. So this has 3 carbons, 5 carbons, 7 carbons, and because they're hydrocarbons, we know that only dispersion forces are possible. Well, if we look at the boiling points, this is negative 42 degrees Celsius. This boiling point is 36 degrees Celsius, and this one is 98 degrees Celsius. So they have the same intermolecular forces, the dispersion forces, but there's clearly a difference in the strength of intermolecular forces, leading to a difference in boiling points. Let's try to picture why. So our 3-carbon alkane is called propane, and let's say this represents a molecule of propane and another molecule and another molecule. And here's our induced dipole interactions. Our 5-carbon alkane is called pentane, and let's say this represents pentane, and then this represents the induced dipole interactions. Our 7-carbon alkane is called heptane, and let's say this represents a few molecules, and then this represents the induced dipole interactions. Now, this is a huge oversimplification, but I use it because it helps to visualize a way to think about the differences. All of these molecules are held to other molecules only by London dispersion forces. And as the molecule gets bigger and bigger, the possibility of these induced dipole or dispersion forces gets bigger. So with a small molecule, we have a small number of induced dipole interactions. With larger molecules, we have more induced dipole interactions. With even bigger molecules, we have even more induced dipole interactions. So in the case of induced dipole interactions, as the molecular weight increases, the size of the molecule increases. As the size increases, the number of induced dipole interactions increases. As the number of induced dipole interactions increases, the strength of the intermolecular forces increases. And as the strength of intermolecular forces increases, the boiling point increases. So even when we have molecules that are held together by the same intermolecular forces, there are factors that are going to make them weaker or stronger. And so with induced dipole or dispersion forces, the bigger the molecule, the stronger the intermolecular forces, and so the higher the boiling point. Let's continue to look at intermolecular forces in nonpolar compounds, and now we're comparing pentane isomers. So remember, these are constitutional isomers that have different connectivity, but the same molecular weight, okay, the same molecular formula, so the same molecular weight. And here we have 1, 2, 3, 4, 5. Here we have 4 carbons in a row and then a methyl branch. Here we have 3 carbons in a row and then a methyl branch and a methyl branch. On the last slide, we saw that as the molecular weight increases, then the boiling point increases. But these all have the same molecular weight, and yet, in terms of boiling point, pentane is 36 degrees Celsius. The next pentane isomer is called 2-methylbutane, and this has a boiling point of 28 degrees Celsius. And the third pentane isomer can be called 2,2-dimethylpropane. This has a boiling point of 9 degrees Celsius. So for nonpolar compounds, if we increase the molecular weight, we are increasing the number of induced dipole interactions, and so that results in an increase in boiling point. But even with identical molecular weights, we can still see a difference. Let's think about the shapes of these molecules. Because this one is a straight chain, down here we have a space-filling model of pentane. This one has a branch, and so this space-filling model has a little kink in it. And then this one, it's kind of this ball shape. What we're looking at with pentane is this. With the 2-methylbutane, it's going to be a blob kind of like this. And with the 2,2-dimethylpropane, we have blobs like this. So with our induced dipole interactions, we have a little bit possible here, we have more here, and we have even more here. So for molecules with the same molecular weight, the surface area has an impact on the boiling point. That's because as the surface area increases, then the number of induced dipole interactions increases. So the strength of the intermolecular forces increases, and so the boiling point increases. So this is more spherical, so a smaller surface area, so less space for these induced dipole interactions, and so overall weak intermolecular forces and a low boiling point. By the time we get up here, because this is more spread out, it has a larger surface area, more room for these induced dipole interactions, which increases the strength of the intermolecular forces, leading to a higher boiling point. We've just seen some comparisons of relative strength of induced dipole interactions depending on the particular molecules. But let's look at different molecules that are held together by different types of intermolecular forces. So here we have propane, and a molecule of propane is held together with another molecule of propane by induced dipole interactions. Dimethyl ether is held together with another molecule of dimethyl ether by dipole-dipole interactions. And ethanol will be held to another molecule of ethanol by hydrogen bonding, right? No dipoles, so only induced dipole interactions. Here we have a bond dipole, and when we consider the shape, we know that there's a molecular dipole, so we have dipole-dipole interactions. And in the case of ethanol, because we have a hydrogen directly connected to an oxygen, that means hydrogen bonding is possible. Now, if we look again at the boiling points of these compounds, propane has a boiling point of -49 degrees Celsius. Dimethyl ether, its boiling point is -24 degrees Celsius, and ethanol has a boiling point of 78 degrees Celsius. So what this shows us is that induced dipole interactions must be the weakest because they can be broken with the least amount of energy. Dipole-dipole interactions are stronger than induced dipole interactions because more energy is required to break apart the dipole-dipole interactions. And then hydrogen bonding interactions must be stronger than the dipole-dipole because a lot more energy is required to interrupt the hydrogen bonding and to separate these molecules. So induced dipole interactions would be the weakest. Dipole-dipole interactions are stronger than induced dipole, and hydrogen bonding interactions are stronger than the dipole-dipole. Now, technically, all molecules are capable of induced dipole interactions. So dimethyl ether has induced dipole as well as dipole-dipole interactions. Ethanol has induced dipole as well as dipole-dipole as well as hydrogen bonding interactions. But we focus on whichever one is the strongest. And so we don't focus on the fact that there's induced dipole interactions here. We focus on the dipole-dipole because those are stronger. In general, we wouldn't talk about the induced dipole interactions because the hydrogen bonding is much stronger. There will, of course, be some exceptions. We'll come to those later. So as we think about the relative strength of intermolecular forces, hydrogen bonding interactions are the strongest, followed by dipole-dipole interactions, followed by induced dipole interactions, or dispersion forces. Now, as we compare the following pairs of compounds, we're looking at ethane compared to methanol. Remember when we were looking at induced dipole interactions of hydrocarbons, we saw that size affects the boiling point. So if we are trying to compare within one type of intermolecular force, we can look at different sizes. But if we're trying to make comparisons between different intermolecular forces, then we want to stick with the same molecular weight, or as close as possible in terms of molecular weight. So if we compare ethane with a molecular weight of 30 grams per mole to methanol with a molecular weight of 32 grams per mole, then we're actually comparing the strength of the intermolecular forces. Now this compound over here has 10 carbons and it weighs 142 grams per mole. If we were to compare this compound with this compound, now we're making changes to the size and to the type of intermolecular forces, so it's like we're comparing apples to oranges. So let's come back to comparing apples to apples, and we're comparing these compounds that have similar molecular weight but different intermolecular forces. Ethane would be held together by induced dipole interactions, where methanol would be held together by hydrogen bonding. And the boiling point of ethane is -89 degrees Celsius compared to 65 degrees Celsius for methanol. So we're looking at a 153 degree difference. So the hydrogen bonding is significant and it makes a huge impact on the strength of the intermolecular forces. Now, if we look at this pair of molecules, 142 compared to 144 grams per mole, once again, this molecule would be held with other molecules by induced dipole interactions, and then this one is capable of hydrogen bonding. And for these molecules, the boiling point is 174 degrees Celsius compared to 215 degrees Celsius. So between these two compounds, our difference is 41 degrees. Here, hydrogen bonding led to a 153-degree difference. Here, it's only a 41-degree difference. So the hydrogen bonding is a little bit less significant in this case. So we have to think about the big picture. This part of the molecule is capable of hydrogen bonding, but the rest of this can't do hydrogen bonding. So a lot of this has to settle for induced dipole interactions. Another way to think about it is that when we have a large molecule, even though it's only capable of induced dipole interactions, a lot of induced dipole interactions really add up, leading to a relatively high boiling point. So now we have defined the different types of intermolecular forces, and we've seen some examples of making comparisons. So we need to keep in mind the relative strength of intermolecular forces, and we also have to consider the different things that impact the strength of intermolecular forces, especially when we're talking about induced dipole interactions. So if you are asked to predict the relative boiling points, for example, or to predict whether something will be soluble in water or soluble in an organic solvent, then what you want to do is take a look at the compound and identify what type of intermolecular forces is possible. If you're making a comparison between two compounds that are both held together by induced dipole interactions, then you want to look at the size. And if that's the same, then you want to look at the surface area. So by taking these into consideration, as well as the size and then surface area, we can make a lot of comparisons and predictions about physical properties.